Okay, I'm supposed to go through this with you, right? Oh, wait, how come? Why doesn't it? What happened? What did I do? Okay, so let's look at this. Sorry, All right, so quickly, check point 11. So can you tell me what is the principle that you have used to derive the answer? What's the principle? So you have your ammonia and your ammonium ion, right? What is their relationship? Ammonia and ammonium, what is their relationship? Yeah, they are conjugate acid-base pair. So pKa of the acid plus pKa of the base, for this conjugate acid-base pair, it will be equals to 14. So because of this, then you can easily arrive at the answer as Denmark. Right? So this is the chemistry principle behind. Can? All right, for question number 2, what's the answer? So first of all, you need to recognize that you are to prepare a acidic buffer. Okay, pH 5 means that it's less than 7, right? You are preparing an acidic buffer. So acidic buffer means what? You need the weak acid and its salt, okay, or rather the conjugate base. Okay, large reservoir of the weak acid and its conjugate base present to make up this buffer. So which one fits the description here? Which one? Yeah, Canada. So the answer is Canada. Wow, Cheng Hao, very good. Why? So let's look at question 3. All right. So which of the following have a pH greater than 7? So number 1, does it have pH greater than 7? Yes or no? Okay. So you see this. This is what is ethyl amine? This is called ethyl amine. So this is a weak base. How you know this is a weak base? Yeah, it's the lone pair on the nitrogen that accepts a proton from your water. So whenever you involve a nitrogen lone pair accepting a proton from water, that is a weak base. So this is the conjugate acid or the salt. Okay, so now you see, right? You have one mole each. So are they large reservoir? Yeah, they are equal in ratio. So in this case, this will mean what? Any special meaning behind equal concentration of your weak base and the salt? Yeah, it's a buffer and it's operating at a maximum buffer capacity. All right, so when it's maximum buffer capacity, what does it mean? What does it mean? So remember, you are talking about a weak base here. So it will be POH. Weak base, what you can calculate first will be POH. It will be equals to PKB plus logarithm of the salt over concentration of the weak base, right? So this is how you can calculate the pH of a buffer, all right? So when this fraction over here is 1/1, what does it mean? Buffer, this is a buffer and it's operating at maximum buffer capacity. And in this case, right, this whole thing will become 0. So POH will be equals to PKB. In other words, pH can be calculated by 14 minus 3.38, which is obviously larger than 7. So therefore, this is the answer. Correct? Get me? All right. So this is not just a buffer, but operating at maximum buffer capacity because the salt and the weak base equal in concentration. So as a result, right, POH equals to PKB. Okay? Can? All right. So let's look at option number 2. So what is option number 2? What's so special about option number 2? Is it a weak acid, weak base, or is it a salt, or is it a buffer? What is it? Yeah, it's a salt, right? There's no weak acid or weak base. What you see here is a salt. So when you look at the salt, you must consider hydrolysis. So can this salt undergo hydrolysis? So Sai, what do you think? Can this salt undergo hydrolysis? Yes, how you tell? Huh? NaCl? Are you awake? So this salt, the parents, who are the acid and base parent forming this salt? Yeah, the sodium hydroxide, which is a strong base. Then who is the acid that forms this salt? Phenol. All right, so phenol from organic chemistry, you know that is a weak acid. Or since you are given a pKa value, it will imply a weak acid. Yeah, so being a weak acid, strong base, right? What kind of salt you have? What kind of salt you have? Yeah, basic salt. Okay, so if it's a basic salt, you will expect pH larger than 7. All right, so therefore option number 2 also correct. All right, so no need to calculate because you cannot calculate at this. There's not enough information for you to calculate. Yuelin, guess what is the issue? Huh? You did the tutorial. Oh, can you pay attention to this first? Thank you. All right, so let's look at question 3. Question 3, what kind of pH do we have? Question 3, acidic. Why so? Because the parent is aluminum hydroxide, which is N equals to 3. So it's a weak base. Then nitrate must come from nitric acid, which is a strong acid. So because of this, right, I know that I'm going to have acidic salt. So this acidic salt means that it's going to release H+. Therefore, pH will be less than 7. So therefore, 3 is not the answer. Can? Oh. Is it okay? Am I going too fast? Yeah? Okay, so we are done with this part. Then I'll move on. Oh, so the answer here is Canada. 1 and 2 only. Okay, let's move on to the next part. Okay, so this page 35, I will not go through with you. Okay, later on you can do your group discussion. Okay, so let's look at this part first. All right, so for page 36, okay, so please take note, during titration, the chemical composition of your reaction mixture will change. Okay, and you will form different type of reaction mixture. For example, buffer or salt solution during different stages at the different stage of your titration. Okay, so therefore you will need the help of this ICF table. ICF table to help you identify what type of reaction mixture at this particular stage of titration. Okay, have you formed a salt or have you formed a buffer? All right, so we are going to look at that. Okay, so step number 1, write the balance equation that represents the acid-base reaction. So when you write the equation that represents the acid-base, please take note. The arrow you need to use is a complete reaction. Okay, for example, I have a sodium hydroxide reacting with HCl in a typical titration to form sodium chloride and water, right? This acid-base reaction will be represented by a full arrow. Okay, so do you know when you should use the reversible arrow? When? How do you know? Yeah, when it's a weak acid or a weak base or a salt that undergo hydrolysis. So basically, right, what is common among all this is proton transfer with water. Okay, so if you have water involved in donating the proton or accepting a proton, then you use a reversible arrow. Can? Sorry. Okay, next. Calculate the amount of reactant used and identify the limiting agent. So in this case, right, before equivalence point, which one is limiting? Because there are two solutions. One will be located in the conical flask, right? So that is pipetted inside into the conical flask. Yeah. Then the other one will be in your burette, correct? So before you reach equivalence point, who is limiting? Before you reach equivalence point, who is limiting? The solution from the burette is limiting, because the solution from the burette is always added dropwise. So every drop from your burette will be reacted away, okay, by the excess solution here. Okay, so before equivalence point, the solution in your conical flask is always in excess. Okay, while burette, the titrant, is limiting. Okay, so when it's limiting, then everything will be fully reacted away. So at some stage, you may form a buffer, depending on what type of acid and base reaction you are carrying out. Okay, then when it's equal, all right, so in this case, right, if you have equal molar of the acid and base present in the reaction mixture, what will you form? What will you form? If let's say you have 0.01 mole of sodium hydroxide plus 0.01 mole of your hydrochloric acid, they react in equal molar, right? Completely neutralized, none in excess. So what kind of solution do you form? The salt solution. So this will become the salt solution. Okay, then after equivalence point, you will continue to add your titrant, right? Let's say you continue the titration, then your titrant will become excess. So the titrant when become excess, you have to check whether this titrant is a base or acid. Then it will tend towards the pH of the titrant value, titrant solution. Can? All right. So therefore, after you have calculated the ICF, you have to classify the resultant solution into this category. Okay, and then use a different approach for calculation. Okay, so after you have identified what type does this fall under, then you will quote the relevant mathematical expression to calculate your pH. Okay, all right, so this is what you're going to do. So this one is with reference to your page 35. Okay, all these are with reference to your page 35. So I'm going to divide you into these groups. Can you quickly move into these groups? Okay, so G1 is graph number 1. I'll give you a graph to look at later on. Okay, so can you quickly shift around? Come on. I count of 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so get your chair, get some chair, so that you can face each other. Okay, don't back face, face each other for discussion. Anyone may ask me, okay, then you look at the page with more words. Because I've decided to ask you to do more things. I mean, I think try to explore more. Okay, can you face each other? Okay, anyone without this worksheet? Anyone else without this worksheet? Okay, so this worksheet, right, requires you to discuss on the titration curve. So like what I've mentioned, right, the top paragraph, during the titration, as titrant is progressively added to the acid base, the chemical composition will change. So therefore, we use ICF table, right, to determine what is the chemical composition. The approach to calculate pH at different points will also differ. So with reference to 35, I would like you to see okay, so what is the purpose of this diagram? Is for you to see that. Okay, so I've tried to use a diagram to show you the different stages of titration. Then I need you to see that before you start titration, this is the initial pH. Okay, so this is what happens during the titration before you attain the equivalence point. Okay, then this is exactly the equivalence point. Then this is after the equivalence point when you add titrant in excess. So the graph is trying to correspond to the pictorial representation. Can? Okay, I'm trying to match up so that you can visualize the titration part versus the titration curve. Okay, so in your groups now, can I request that you try to fill in the blanks and also try to identify how you will calculate the pH at different point of the titration curve. Can you do so now? Can you do so now? Yeah, I'll give you 5 minutes. Huh? If you look at the volume, this is a title level. So at 0 is no titration. So when it's 1, it means that you have added 1 cm.
It's supposed to be an arrow of more than.
Huh?
This is supposed to be an arrow, right?
Arrow, arrow.
Oh, this.
The arrow. Yeah. I just put hyphen, hyphen, then direct.
I thought it was.
No, it's not. Hmm? Oh, no, it's you mean this two?
No, this one.
This one.
Example,
Yeah, so this one is not applicable here lah, because I hope you can recognize that what kind of acid-base titration this is. Okay, anyway, so this one is maximum buffer. It can either occur at half x or 2x. So x is the volume at which you attain equivalence point. So it can either be half of it or twice of it. Explain. Yeah. Why is it half or twice? It depends on what is in your conical flask. Because you need the conjugate acid-base pair of a weak acid and a weak base in large reservoir. Yeah, so it really depends on what is in your conical flask, what is present in your burette added to the conical flask. Yeah, so the large reservoir of the conjugate acid-base pair may occur before or after equivalent point, depending on what you put inside your conical flask or burette. Yeah. Finish?
Yeah.
Now you have soccer training almost every day. Is it? But your competition is tomorrow, then you have practice almost every day. Yesterday got, and today rest. Huh? No, astronomy only astronomy only also practice more. And theory. Oh. Okay, time's up. So in this case, right? Okay, so I will fill in the blanks first. So if I'm not clear, please tell me or clarify with me. Okay, so this is where the initial pH is. Okay, so this is initial pH. How do I know this is the initial pH? Because this is where 0 cm cube of your titrant is added. So the solution inside your conical flask is the pure acid or pure base to start with, before the start of titration. Okay, so to calculate this initial pH, right, which part of the page 35 equation should you use? Which part of the page 35 equation should you use? Which part? Yeah, so strong base. Okay, how do you know this is a strong base? pH 14 means it's a strong base. Is that must be always true? At 25 degrees Celsius, what else? Is it always true that high pH reflects strong basicity or 100% dissociation? It depends on the concentration as well. So in this case, right, no doubt, there is a high pH, but we must be open to the fact that it might be a strong base or a weak base. So in this case, either case A or case B is applicable. Okay, so this means, right, for this part of the calculation, okay, you can either use the strong base approach because the starting is a high pH value, right? So this means that your conical flask contains what? What's inside your conical flask? The base. It must be the base inside your conical flask. Huh? So strong base, it will be this approach. If it's a weak base, then it will be this approach. Okay, we must be open to that first. Okay, we can't tell whether it's strong or weak base unless the question tells so. All right, Ken? So after we are done with this part, then we start the titration, because you see that as you add 1 cm cube, 2 cm cube, 3 cm cube, the pH will start to change, right? As part of the OH minus is being neutralized by the acid added from the burette. Okay, so it's a gradual change. So it will be a gradual change until before the last drop of your the analyte is used up. So in this conical flask, you will still have the last drop of base. So before this last drop of base is used up, is about to have a steep change. Okay, so as long as you have one last drop, it should still stay in the alkaline region. Agree? As long as you have still one last drop of OH minus in your mixture, it should still stay in the alkaline region. But the moment the last drop of OH minus is used up, okay, it will undergo a drastic change. Then the next part will be one drop of your titrant, one drop of unreacted titrant. So this unreacted titrant will cause the pH to drop very low. Okay, so I'm trying to explain to you why is there a drastic drop. Before one drop is used up, still alkaline. After that one drop is removed, with one extra drop of titrant, become acidic. So that's why there's a steep change here. Okay, so at this moment, there is a pH here, indicated here. So this is the pH caused by what? Yeah, it's a salt. All right, so of course, this is a pH 7. So what does it mean? Yeah, it's neutral. That means it doesn't undergo hydrolysis. No hydrolysis, right? Since pH is neutral, midpoint of this pH, midpoint of this steep change is neutral. So this means that the salt doesn't undergo hydrolysis. No hydrolysis. So if it's no hydrolysis, what does it tell you about the acid and base? Yeah, it must be a strong acid, strong base titration. It's only when the both parents are strong, it gives you a child neutral, right? Okay, so that will go back to the first point. Initial pH is caused by the strong base, therefore you use a strong base approach. Okay? So how do you calculate the pH caused by this salt if there's hydrolysis? If there's hydrolysis, how do you calculate? What is the approach if there's hydrolysis? Then it will be case C. Okay, with reference to your page 35, it will be your case C. Case C. Then in this case C, right, please take note, you have to consider dilution. Okay, why is there dilution here? Can someone tell me? Why is there dilution here? Why is there dilution here? Oh, sorry, it's very small now. Sorry, you should tell me, Alma. Okay, so in this case, why do I need to consider dilution here? What do I mean by dilution? No? Did we add water during this titration? No, we didn't add water. But what are we doing? We have volume of base in the conical flask, right? So if I use 25 cm³ pipette, then I will start with 25 cm³ of base in the conical flask. Then as I add solution from my burette to the conical flask, will the total volume increase? Yes, so this is what I meant. Yeah, so the total volume would have increased. Why increase? Because you have 25 cm³ here, and you keep on adding your titrants. Okay, so let's say the equivalence volume is X. Okay, so the value X here is the equivalence volume. The volume of titrant required to fully neutralize your base. Okay, right, so this is the value of X here. Okay, so the total volume now becomes 25 plus X. Okay, so your salt produced is now in a total volume of this. Okay, so when you calculate the concentration, you have to consider dilution. This is what I meant. Ken? So far, so good? Yep. Weak acid? No. Weak acid, weak base, meaning? Of course, same. Yeah, everything is same. So it doesn't matter what is the strength of the acid or base, as long as you carry out a titration, you are increasing the total volume of the mixture. Yeah. So at equivalence point, you are able to calculate the total volume and you can calculate the new concentration. Yeah. Okay, so let's look at the last part. Yes, sorry. Oh, we don't learn weak acid and weak base. We only learn 3 categories: strong acid, strong base; weak acid, strong base; weak base, strong acid. Yeah, only these 3. Can? All right, so let's look at the after equivalence point. After equivalence point, the pH will tend towards. So this is the arrow, is tend towards. So it will tend, is an asymptote. Okay, it will not reach that value, but it will tend towards that value. It will be tending towards the pH of your titrant when your titrant is in excess. So of course, in this case, your titrant refers to the strong acid in this case. Okay, that's why you can see that it's approaching a very strong acid pH. Can? That is after equivalence point. Can? All right, so next part. Okay, so let's look at the bottom of this part. So when weak acid or weak base is involved, of course, for this titration curve, do you see a buffer? For this titration curve, will you be able to form a buffer? No, because in this titration, is involving strong acid and strong base. There's no weak acid, there's no weak base. So there's no buffer here. There's no buffer at all in this titration curve. Okay, all right. So later on, the graphs that I'm going to ask you to work with, right, there is a buffer region. So I need you to help me identify where is the buffer region. Okay, so in this case, right, if there is a weak acid or weak base involved in titration, a buffer can be formed. Only a reaction mixture with large reservoir of what? Yeah, conjugate acid-base pair of weak acid and weak base can be a buffer. Okay, so can you help me fill this in? It must have conjugate acid-base pair of a weak acid or weak base present. And the max buffer can occur at either half the equivalence volume or twice the equivalence volume. Okay, so later on when you do your discussion, you can better appreciate that. Okay, so as mentioned, if your ratio of salt and weak acid is 1, then the pH will be equals to pKa. So if you are talking about alkaline buffer, then pOH will be equals to pKb. Right? Okay, this is what we have talked about earlier on when we go through the checkpoint. All right, so that is maximum buffer. Yes. So later on, when I give you the graphs, you can work together. Okay, so according to this, right? Okay, so later on you discuss. Okay, so this is what we are done. Any question? Anything that you need me to clarify before you work on other graphs? This one don't have because it's a strong acid, strong base. Other scenario, you work on it, then you see. Okay, so the next part, right, is about the indicator. So indicator basically is quite easy to understand. I mean, to me. So your indicator itself is also a weak acid or weak base. Okay, so the indicator will also undergo partial dissociation to give you H plus and IN minus. Okay, so you are told that the indicator in the molecular form or in the anionic form, they have their own characteristic color. For example, if the molecular form is red, then the anion form can be blue, for example. Okay, for example only. So in cases whereby you have a highly acidified medium, okay, where the H plus concentration is high, this will mean that the POE will lie on the left. So what does it mean? You will see more of the red, less of the blue. So when you place this indicator in an acid, right, you will see red instead of blue. That's what it meant. Can? All right. So of course, when you place the same indicator in alkaline solution, what will happen? In alkaline solution, the H plus concentration will become very low. In alkaline solution, H plus drop drastically, right? Then it will shift forward. So POE will shift to the right. So this means what? You see, what will you see? When this indicator is placed in the alkaline solution, what will you see? You see more blue than red. Yeah. Okay. So when it's in between, then what you see is purple, so-called. So that is the working range. So later on, you are seeing this table over here. This table over here tells you what is the working range of each indicator, because the POE of indicator is unique to each. They have their own acid strength. They have their own K indicator values. Okay, so this will be the working range. Now, for this tree, right, you need to roughly recognize that the working range for methyl orange is within the acidic region. Okay, so can you help me remember methyl orange? The working range is in the acidic region. Okay, 3 to 5. If you can remember, like acidic region 3 to 5. Okay, for phenolphthalein or thymophthalein, right? The acidic, the working range is in the alkaline region, 8 to 10. Okay, so just remember that first. So if you look at the pictorial form, this is what is shown. So across the pH scale, methyl orange will start changing color from 3 to 5. Okay, so you notice that it's a mix of the two extremes. Okay, so for phenolphthalein and thymophthalein, is from here to here. So it's a mix of the two extremes. Okay, so this is what you are going to observe at the endpoint color change. Okay, so you don't see the two extreme, because once you see the two extreme, it means that you add excessive, not the equivalence point. Okay, so you should be seeing somewhere in between. So with this in mind, okay, so there's a very popular A-level question. They will ask you, okay, why do you choose this indicator? Why do you think this indicator is suitable? All right, then I need you to quote this as the answer. Okay, the answer is, indicator for acid base are chosen such that the working range of your indicator falls within the steep pH change of your titration curve. Okay, so whenever they ask this type of question, you just regurgitate this answer. This is the standard answer. Can. Okay, very quickly, right? Let's start the titration curve. So before I continue with the discussion, I would like to ask this. There's these two questions at the bottom of your handout. Okay, so titration above involves a strong acid, strong base. So in this case, you should know that you cannot depend on, cannot tell from pH value alone. Right? You cannot tell from pH value alone. Okay, in order to deduce strength, you have to compare H plus versus the concentration of the weak acid, concentration of the original acid, or OH minus versus the concentration of your base. Okay. Okay, second question. In this case, are you able to see that both indicator can work for this titration? Yeah. So do you notice that in this graph, the working range of your phenolphthalein and the working range of your methyl orange, it coincides with the steep pH change. Okay, so this will tell you that both indicator can be used to tell you the equivalence point. Okay, they can work. So any other question about this part? All right, so if there's no other question, then I'll hand you the different handout. Then remember the allocation that I gave you just now. So there are 4 graphs over here. So I need you to work with the different graphs. Okay, so these graphs will have a buffer point. So I need you to discuss in your own groups, right? Where is the buffer point? Pass down, pass down. Okay, so Yuelin's group will be doing graph number 1, Sebastian graph number 2, Zhenhan graph number 3, so on and so forth. So the G is telling you which graph you are working on. So you are just working on one graph. Extras? Is there any extra floating around? No more. Huh? Okay, so can I give you like 10 minutes to work on it? Two times is because is the other one. This one will be 2 times. Yeah. I say either or, not both. You are to answer the questions at the side. There's a list of questions at the side, right? Help me answer that.
Like how to reduce the strength, because it feels like when you look at this pH which is lower,
Yeah.
then it naturally feels like
No, it could be my starting base, even a strong base, but of a lower concentration.
Oh.
Yeah. So a lower concentration strong base can also give rise to this. So you cannot be too quick to conclude that it's a weak base.
But then how are we supposed to deduce this from this?
So that one more of the tutorial question they will show you how. So they will give you the H plus or pH value for you to deduce H plus concentration. Then the titration result will enable you to find the concentration of the acid, the whole thing. Then when you make a comparison, you can deduce out the acid level. Yeah. So it depends on the context of the question. Yeah.
But then in this context, how are we supposed to whether like
Yeah, from here.
oh
Yes. What?
So this one, right? Okay, the equation
Yeah.
is the acid base, then the acid plus salt, conjugate base plus weak acid.
For number 3?
Yeah.
Number 3, you're talking about salt hydrolysis, right? So
Yeah.
number 1, what sort of salt are you looking at?
Basic salt, conjugate base.
Basic salt. So basic salt, it must be the anion undergoing
No,
hydrolysis.
as in,
Yeah, so I mean, I did not give you the identity of the acid. You can think of one example yourself, or you can use a generic A minus.
HA lah, yeah lah.
A minus.
Wait, so then when it's A minus.
Yeah, because it's the anion that undergo hydrolysis to release the OH minus.
So this equation is the hydrolysis equation.
Yeah.
So the front here is the left side is A minus plus H2.
Yeah.
what's the steep thing occurs after the So halfway through, that's what you're adding and what you're getting. Yeah.
This is from the buffer solution is from the salt.
Buffer solution must have equal concentration of the weak acid and the salt, or weak base and the salt. I mean, large
So the
reservoir.
weak base comes from the original thing, right?
Yeah, so this one, initial pH, not you start from low pH, right? So this means what? What is inside the conical flask?
Acid.
Yeah,
I know.
it's acid.
So no, I'm asking like the buffer solution is formed only after equivalence point or what?
Why? What makes you say that?
Because before the equivalence point, there's no salt form. What?
Before equivalence point, there's salt. When you add alkali reacts with the acid to form the salt.
The what happens is
When
fully
all,
used up.
yeah, fully used up. Yeah,
But
so
before-
100% salt.
but before that, there's already like increasing of the concentration of salt.
Yeah, as your acid
Which
decreases, your salt will
forms the
increase.
buffer lah.
Yeah.
Then how you see the effect of the buffer?
What do you mean?
Because buffer counters
phase change, right?
Yeah, so that's why here, right, it's a very gentle change. It looks like there's an
I
inflection
thought it
point.
would be like this constant.
Yeah, but then this pH change is not exactly constant, so there will be an inflection point. Right? So there will be a point at which like it's very slow. The change is very slow.
Like it's suppressed.
Yeah.
So throughout the whole
Mm.
process, there's
Yeah.
always a buffer. There's always a
There's
salt.
always a buffer, but at midpoint it will be the max buffer capacity.
Where?
At the mid, so let's say this is X, right? At half X, it will be max buffer capacity. Because it's half neutralized, means half of the acid still left behind, half salt.
1 to 1.
Yeah, 1 to 1.
Okay, so do you need more time? Need more time. So for those groups who are done, right? Can you help me vote with the groups which are still discussing? Are you more or less done? I give you 2 more minutes. Can? Okay, if you're done, you can discuss with your neighbors. Because they are discussing different graphs, you can discuss. The two of you, okay? Then you want to help them? You have a question to ask? You can ask. No question? Okay, I think more or less ready, right? Okay, so we'll just cut short. Okay, let's look at the worksheet together. Okay, so whether it's acid or base in the conical flask. So in this case, I will answer across the 4 graphs. So whether it's acid or base in the conical flask, you have to refer to the initial pH. So this is an alkaline pH. So this will mean that in your conical flask is your base. Okay, so alkaline pH, same thing. This is your base. So for graph number 3, you started off with the acidic pH. So in a conical flask, your acid. Then again, acidic pH, conical flask contains your acid. Okay? Now, but at this point of time, you still cannot tell the strength of the acid or base since you're not given the initial concentration of the acid or base. Yeah? But you can tell from where. How you know the strength of your acid or base? Yeah, the salt hydrolysis. So for graph number 1, you notice that this pH falls below 7. So this is an acidic salt. So if it's an acidic salt, then it must come from a strong acid, weak base. Okay, so this is your weak base in the conical flask. Your strong acid is added from the burette. This is how we conclude. Okay, without the initial concentration, I can still use the pH value at equivalence point to deduce the strength. So same thing for graph number 2. I noticed that the pH value is more than 7. So this means what? It's a basic salt. So basic salt means what? Strong base and weak acid. So this is my strong base in the conical flask. My burette will contain the weak acid. Okay, so this is how you visualize your titration. Okay, so similarly, if you look at the next part, the equivalence point here is less than 7. So this means that it's an acidic salt. So this is a strong acid. Then this is your weak base. Logical? Okay, so if you look at the last one, your pH is more than 7. So it's a basic salt, strong base. So strong base is in your conical flask, but strong base is in your burette. Then your weak acid is in the conical flask. Okay, so far so good. All right, so then after that, we are supposed to write the equation, right? So let's settle the equation first. So for the first equation, acidic salt. Okay, acidic salt, this means the cation must be the one undergoing hydrolysis. So if I take to be a conjugate base of a weak acid, this is the typical conjugate acid of a weak base. Okay, conjugate acid of a weak base undergoing hydrolysis, this is what you will obtain, okay, in the equation representing or trying to explain pH 7, hydrolysis of the cation. Then hydrolysis of the anion. So anion here, you can use a generic A- to react with your water to undergo hydrolysis to create HA or OH- release, or you can use whatever that you have learned in the notes as an example to write the hydrolysis equation. Also can. Okay, so remember, any proton transfer with the water is a reversible error. Okay. Then the other two I will not show up because it's the same. And the next two graphs, the equation is the same. All right. Okay, so let's look at the buffer region. Okay, so in this case, right, where is my buffer? Where's my buffer? Okay, so those who are doing graph number 1, can you tell me where is the buffer? If let's say this is X volume, where is my buffer? Half X or 2X for maximum buffer? Yeah. So the region is before equivalence point or after equivalence point? Huh? So for graph number 1, where is the buffer? Before X or after X? I thought you all have done your discussion. Graph number 1. Hello. Huh? Where is your buffer? Before X or after X? Before X, huh? Okay, before X. Why so? It's because before X, as your weak base progressively becomes the salt. In this region, you will have a mixture of weak base and the salt. Okay? So remember, your weak base is progressively being neutralized to become the salt. So within this region, you have weak base and the salt together. So that is the component of a buffer. And where is the maximum buffer? Maximum buffer is when it's half neutralized. When half of your weak base becomes the salt, then that is when the concentration of the weak base and the salt are equal. Okay, at half equivalence point, this means that only 50% of the weak base has become the salt. So at that point, your weak base and the salt 1:1. So that is the maximum buffer. So what is this? What happens after this? What happens after this is you only have the salt and strong acid. So does it meet the component of a buffer? Don't have, because there's no weak acid here, only salt. Okay, so after equivalence point, there's only salt, no weak acid, no weak base. So no buffer here. Okay, is it clear? So as long as the buffer is before equivalence point, half X will be the max buffer. Okay, all right, so let's look at the next one. Graph number 2, where is the buffer? After X. Okay, why so? Why so? So during this process, right, you only have a strong base present and it's progressively converted to salt. So within this region, what do you have in the mixture? Only the strong base and the salt. So strong base and the salt got buffer? Don't have. So after X, what happens? After X is when you have the salt still there, but you will have excess of the weak acid added as a titrant. Yeah. So this is where you start your buffer system. So as long as the buffer system is after the equivalence point, the max buffer will occur at 2x. And okay, so do you need me to explain graph 3 and graph 4? No need, huh? So we are done with this part. So I hope that you have learned something from this group discussion. For those who are helping me teach the rest, thank you very much. Yeah. Okay, so let's go back to the content. Any question? Have I clarified all the doubts? Do you have any question to clarify? Huh? Oh, the shape no difference. I don't expect you to show a difference also. Yeah. So basically, at the max buffer, right, it's like an inflection point. Whereas if it's a strong acid, strong base, right, it's a gradual change. I mean, my drawing not very nice. Yeah. Inflection point. So at the max buffer, right, the dy dx equals 0. Okay, whatever. Okay, so blah blah blah. All right. In this case, oh, I forgot one question. The last question. If I replace the strong acid with a weak acid or strong base with a weak base, will the titration result be affected? No, it will not be affected. Why so? Extent of dissociation is the same. No, weak acid. It doesn't matter here. Why doesn't it matter? Yeah, because of the acid-base reaction, it will, based on the Chatillon principle, keep on shifting forward. Yeah, so even if you replace with a strong acid with a weak acid or strong base with a weak base, it will not affect the titration result according to the Chatillon principle. Okay, right. So if you go back to this page again, page 39 of your notes, and I want you to superimpose a graph on the strong acid, strong base. What do you notice? Do you notice that the steep change becomes shorter? For strong acid and strong base, because you start off with two extreme, right? Very high pH, very low pH. So the change is much steeper compared to when you start with a weak base or when you end off with a weak acid. You notice that? So what do you think is the significance? What's the significance? Huh? Yeah, so if you are talking about the strong acid weak base, can you choose phenolphthalein as your indicator? Strong acid weak base, the second one. Let's look at this, huh? So when I have this, can I still use phenolphthalein as my indicator? Cannot, because the working range of your phenolphthalein is no longer within the state change. All right. And if you use phenolphthalein, what will happen to your titration result? Yeah, it will become less because it will change color from this point onwards. Do you see that? According to this titration curve, the working range of your phenolphthalein will start changing color from this point onwards. So it will give you a titration result, which is much smaller than the correct answer. Yeah, so the choice of indicator is very important. Ken, does it make sense? Yeah, so if you look at the next graph, can you use methyl orange as your indicator? So can you tell me what will happen if you use methyl orange as your indicator? It will never reach endpoint because it will never change color. So if you look at the weak acid strong base titration, right? Notice that the working range is below the asymptote. Yeah, right? The plateau. Yeah, so it will never change color. So for this case, right, you must choose phenolphthalein or thymophthalein. Okay, because both phenolphthalein and thymophthalein, the working range is in the alkaline region. Yeah, Ken? Am I making sense? All right, so if I make sense to you, right, then the next part is all what you have done so far in your group discussion. So you can read on your own, blah, 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 blah. So I just want to emphasize this part. Okay, for buffer region before equivalence point, it will be half the volume. Okay, and what is the pattern? The pattern is whenever you have the weak acid or weak base in the conical flask, then it will occur at half V. Okay, this is the pattern. Right? So if it's after equivalence point, then it's likely that your strong acid, strong base is in the conical flask. Then it will be 2V. Okay? Right? So this one is on, yeah. So can you help me highlight that to reiterate? Page 41. Okay, can you help me highlight? So half V when weak acid, weak base in the conical flask. 2V when strong acid, strong base in the conical flask. Okay, so this is for you to think faster. Of course, you can still think on the spot. Okay, Ken? All right, so for example 11, I will not go through with you. I think some of you are more or less ready to calculate. So can I ask you to work on checkpoint now? Then I'll go through the checkpoint. Yeah, very fast, very happy. Okay, so let's work on checkpoint 12 now. You can work in a group, then I'll go through the answer. NH3, the nitrogen lone pair. So it's a weak base or strong base.
I hope you understand the phrasing. When A is titrated against B, A is by default the control plant. So in this case, HCl is titrated against base. So HCl is in the control plant.
Okay, are you more or less ready? Do you need more time? Okay, more time. 2 more minutes. This one is salt only, so you need to show the salt hydrolysis to account
Also,
for the
this
alkaline
salt.
pH. Yeah, to account for the pH at equivalence point. Done? 30 more seconds. Uh, 40 minus pH is what? What? So you are calculating the pH at max buffer, is it? Oh, pushing that. pH at max buffer?
The next buffer is.
Yeah. Correct.
Yeah.
Sorry. pH. pH.
This is an acidic salt.
Huh?
Yeah.
Yeah.
Oh, it's acidic salt.
You don't know?
No, that
Yeah.
Wrong lah. You are assuming it's a strong base. Is it a strong base? See, I hit you correct.
Hey, can I go through the answer? All right, okay, so let's look at the first part. First part is quite straightforward. I hope you can recognize that when you have solution A titrated against solution B, A will be in the conical flask, while B is in the burette. Can? So you must recognize the phrasing, because you are the one sketching the graph. So you must know whether it's acidic to alkaline or alkaline to acidic. Okay, so your acid is in a conical flask. So this means that you start low, then end high, the titration curve. Okay, so this is how you should visualize the shape of your titration curve. So before addition is just strong acid. So full dissociation. So this one is quite straightforward, 0.3. At the equivalence point, where all the strong acid is neutralized by your weak base added from the burette, then you see salt hydrolysis because you have a weak base involved. Okay, so you will have a acidic pH due to salt hydrolysis. This is the equation showing the salt hydrolysis. Okay, so this is the acid-base reaction representing the reaction taking place during titration. Okay, so this is what occurs during titration. So this is what occurs at equivalence point. Okay, so where is the buffer region? The buffer region will be before or after? After the equivalence point. So before equivalence point, there's no buffer. After equivalence point, you will have your buffer region, because after equivalence, that's where you have a mixture of the weak base and the salt. Okay, then from here, you should know that it's going to form a basic buffer, a weak base and the salt. Okay, weak base and the salt will form a basic buffer. Okay, then how do you calculate the maximum buffer? So the titration result, I hope you can recognize that the volume at which equivalence point is attained is 25 cm cube. Remember? Okay, so at 25 cm cube of the weak base added, that is where your equivalence point is. So you are going to double that equivalence volume. So the max buffer will occur when the titration result is 50 cm cube. Okay, so at max buffer, it will be 14 minus POH, 9.26. Yep. So any question to ask me about this part? Comfortable with this? Okay, so the next part is where you have excess of the weak base added. So remember, this is a weak base. So when you calculate the pH, POH, you have to use this expression, Kb times concentration of your weak base. And this must consider dilution. All right, so if you are really calculating, so the dilution is halved. No, okay. You cannot consider dilution because it's already in excess. Okay. You can just use the original initial. Okay. I delete. So you can just use the original, then it will tend towards this value. So if you do a calculation, it will tend towards this value. Okay, so this is your original concentration of your weak base initial. Okay, then this is POH, remember? So to calculate pH, you have to subtract from 14. Can? Make sense?
You can ask question if I'm not clear. Okay, so how do I sketch my, can I continue? Okay, so when I sketch my titration curve, I will put my 0.3 here. So this is my 0.3. Okay, then this is my equivalence point. This is where my max buffer is. Okay, so at equivalence point, I know that my pH at equivalence point must be less than 7 because it's an acidic salt. So this is where my 7 is. Okay, I just need to indicate where 7 is. And this will be the midpoint of my steep change that is below 7. Okay, then I will roughly have the steep change, the length equal on both sides of the point. Yeah, because it's supposed to be the midpoint, right? So after I indicate the midpoint to be less than 7, then I make sure that the straight line is equal above and below the midpoint. And okay, then the next one that I need to indicate is the pH at which it approaches with excess of your ammonia. So excess of ammonia, this is where aggregation, this is where your 11.48 is. So I will draw dotted line, horizontal dotted line. Okay. Then my maximum buffer is 9.26. So it's about here, 9.26. So maximum buffer 9.26. This is where my maximum buffer is. And then after that, I start joining up the points lor. So I will start joining up there. Woo. It will look like this. Okay, so you need to indicate this is the max buffer. Okay, so this is how I sketch. I put my points first, the volume and the corresponding pH. Okay, all the values that I've indicated is a mass, they are all marking points. So you must label the max buffer, the volume, and the corresponding pH. Okay, you must tell me pH at equivalence point, lower than 7 or more than 7. Then of course the initial pH. Okay, I think that's all for today. So your homework is until question 7. Tutorial question 7, you should be able to do. Tutorial question 7 until all the way from 1 to 7 you can do now. All right, yeah. When is it due? The next time I see you. Tomorrow is your practical. Next time I see you for tutorial is coming Monday. So get it ready by coming Monday, okay? Then after that tutorial, if there's time, I'll go through the poly basic titration. Because there's this part on poly basic titration. Yeah, the next part. Okay, the rest I will not go through with you. There's a lot of words. You go and read yourself. I'm not going to go through all the words with you. Okay. So this is the part that I will want to go through with you if we have time, before you try the other tutorial questions.
equivalence.
Oh, you want to label also can, but I indicated so hydrolysis also, that will mean that it's equivalence.